In tracing the intellectual lineage of modern calculus, one name stands paramount: Gottfried Wilhelm Leibniz. His 1684 publication, New Method for Maxima and Minima Likewise Tangents, represents a pivotal moment, a crystallization of ideas that revolutionized mathematics and, by extension, the sciences. It is an achievement requiring careful consideration, one that demands precise examination of its genesis, content, immediate impact, subsequent evolution, and lasting leg. The intellectual atmosphere preceding Leibniz's breakthrough was ripe with nascent ideas about change and motion. The problem of tangents and the quest to find areas under curves occupied mathematicians for decades. Early attempts, such as those by Fermat, relied upon elaborate algebraic manipulations, often cumbersome and lacking a systematic approach. The work of Isaac Barrow, Leibniz's teacher during his time in Cambridge, provided crucial insights. Barrow's Lectiones Geometricae offered a geometric method of finding tangents, one that hinted at the inverse relationship between tangents and areas. This was a crucial stepping stone, but it lacked the generality and symbolic power Leibniz would later introduce. Barrow's legacy offers a strong foundation, the core of Leibniz's innovation residing, first, in his elegant notation. Previously, mathematicians grappled with cumbersome expressions. Leibniz, recognizing this limitation, introduced notation that proved transformative. He introduced the symbol d for the differential, representing an infinitely small change. Hence, dx signified an infinitesimal change in x, and di indicated a corresponding infinitesimal change in y. The ratio di divided by dx, or dy dx, became the foundation, representing the derivative. This notation possesses many benefits. It made the manipulations of calculus far more accessible. Mathematical statements became concise. Relationships were clearly expressed. The familiar integral sign, resembling a long S, represented the sum of infinitesimal quantities, mirroring the relationship between differentiation and integration. The application of this symbolic language, the essence of Leibniz's innovation, solved mathematical problems. Leibniz presented a systematic method for determining maxima and minima. He demonstrated how to find the points where a function reaches its highest or lowest values. This involved setting the derivative, dy dx, equal to 0. Moreover, developed rules for manipulating these differentials, thereby creating a set of powerful techniques for solving a wide range of problems. The immediate impact of Leibniz's paper was considerable. It provided a practical, efficient toolkit for solving problems in geometry and physics. The method quickly spread across Europe, garnering both admiration and, initially, some hesitancy. Mathematicians recognized its power and began to apply it to diverse situations. The paper provided a method for determining tangent lines to curves and calculating areas. It impacted the scientific world. Scientists now had tools to analyze motion, study the behavior of celestial bodies, and optimize designs. The method impacted many fields of study. The evolution of Leibniz calculus following its initial presentation is a complex and fascinating story. It was rapidly adopted and developed by other mathematicians. Among the most prominent was the Bernoulli family, particularly Jacob and Johann Bernoulli. They built upon Leibniz's foundations, extending the theory and applying it to a greater variety of problems. These included differential equations, which became one of the most important areas of mathematical research. The field grew beyond Leibniz's initial framework. The development of calculus sparked a period of intense activity, with mathematicians refining techniques, exploring applications and grappling with foundational issues regarding reception and critique. Leibniz's work faced challenges, most notably a controversy surrounding the priority of discovery. Isaac Newton had also independently developed calculus. The nature of these discoveries, the development of similar approaches, led to a highly publicized dispute over who first discovered calculus. The debate between Newton and Leibniz, and their respective supporters, was acrimonious and consumed much of the scientific community. This conflict, while unfortunate, highlights the significance of both contributions and the competitive spirit that often drives scientific progress. While the priority dispute cast a shadow, the eventual convergence upon Leibniz's approach, especially his notation, demonstrates the power of his system. The notation offered unparalleled flexibility and clarity. Leibniz's work drew heavily from several influences. He was a polymath, immersed in philosophy, logic, and mathematics. He possessed a deep appreciation for symbolic reasoning and the power of notation. His study of older algebraic techniques, his engagement with the works of predecessors like Pascal, and his personal interactions with mathematicians of his time, notably Huygens, guided his intellectual development. Huygens, in particular, recognized the value of Leibniz' approach and became an early advocate. The reverberations of Leibniz' new method on subsequent generations are profound. His notation is the standard used today. Calculus, as a discipline, has become a cornerstone of mathematics. Its applications extend to virtually every scientific and engineering field. His notation's versatility and efficiency continue to be employed. Calculus is indispensable to physics, engineering, economics, and computer science. The integral calculus is vital in determining areas and volumes, modeling physical phenomena, and solving complex equations. The differential calculus forms the basis of optimization techniques, the study of rates of change, and the analysis of dynamic systems. The modern world depends on the tools Leibniz provided. The legacy of Leibniz' work resides also in its conceptual influence. The ideas of infinitesimals, of continuity, and of change have shaped our understanding of the world. His philosophical works explored the concept of monads, unified substances that reflect the universe. These ideas reflect his mathematical achievements. His calculus provided a powerful framework for describing and modeling natural phenomena. His legacy is a testament to the power of mathematics. In conclusion, Leibniz' new method for maxima and minima likewise tangents represents more than a singular achievement. It stands as a watershed moment. It provided a new method, the beginning of calculus, and his elegant symbolism changed the course of mathematics. His influence permeated science and engineering. His work transformed how we understand the world. It reflects the power of ideas. It underscores the importance of clarity. It is a legacy that resonates through the centuries.